So vectors are pretty easy to deal with, I think. If they're just kind of floating around, we can look at them. And sometimes if we're given a point and another point, and we want a vector connecting those 2 points, we can, if we're just drawing it, that's easy enough to draw. But to actually get the vector and be able to work with it mathematically, I think it would be good to go through 1 or 2 exercises where they resolve a vector. They call it resolving a vector. So I think for sections 12.2 through 12.4 or 5, that hasn't been, I haven't assigned a due date for those yet, right? So I'll assign due dates for that fairly soon. But those are the topics that we're going to be talking about. So what we want to do is we want to resolve some vectors, and then we'll talk about addition and subtraction. And I think I saw some problems that were interesting to work with. I don't know if it was in the homework, but they have some of this. And let's just go ahead and jump right into 3 dimensions and do one of these problems. So let's try this one. We have 2 points. Find a vector A with a representation given by the directed line segment AB. So in other words, what they want to say here is A, little a, and it's a vector, so it's boldface in the way that they would write it, but I would write it with an arrow on top. And this is AB, a line segment that connects these 2 points, A and B. And if you imagine these 2 points, let me just for now randomly put them somewhere in space, and I'm not going to draw the X, Y, Z axes to put it in perspective. I'm just going to draw random points in space. If I want to go from A to B, this is telling me that I want a vector whose head is on B and whose tail is on A. And to obtain this vector, it's a line segment. So if we just imagine putting this line segment back where the tail is at the origin, we're essentially subtracting the tail from both the head and the tail. And if you imagine subtracting the tail from the tail, you're just going to get 0, and that brings you to the origin. So to resolve this vector, you would just do a head minus tail calculation. And when I say head minus tail, it has 2, if it's 2 dimensions, it has 2 components. Here it's 3 dimensions, it has 3 components. We just do the subtraction component by component. And so this is going to give us A is equal to. So the first component minus the first component, and it's head minus tail, so I need to do B minus A. So I got 4 minus 4 for the first one, and I have 4 minus 0 for the second one, and 3 minus negative 2 for the last one. So I have the vector A is equal to 0, 4, 5. And so that's how I'm able to resolve the vector. Now, without drawing this or doing anything fancy, can anybody tell me where this point is? Can you describe where this point might be? I'm kind of looking at the 0 there, and that must mean something if one of the components is 0. Where is this point, or where does this point live? On the what? On the YZ plane. So that's just an observation. We don't need to know that. In this particular problem, which I don't know if it is in your homework or not, but this particular problem is also asking us to look at the graph of this and identify the graph and how it would look like. So let's take a look at the options that they have for this graph. Draw A, B in the equivalent representation starting at the origin. So when we resolve the vector, we want to imagine the vector with a tail on the origin and pointing in the same direction with the same direction and magnitude as the original vector that was out floating around in space. So this choice over here is a vector whose head is at the origin, not the tail, so I want to eliminate that. And so is the next one. So what's the difference between these two, this one and that one? So this one has the vector pointing this way, where it needs to be pointing in the same direction and magnitude. So I'm going to have to go with A for this one. By the way, let's see if we can I just use the brackets like that? Just to make sure, I can probably click on vector here. Here's the vector brackets. Oh, it's a little bit different. Let's see if it'll take my brackets like this. What is it, 0, 4, and 5? Nope, it's not. Oh, there it goes. Let me see if this will take, if I submit it. So you have to be kind of precise with this system. It looks like I was able to get by with the less than and greater than symbols here. Yeah, they took it. In general, though, you know, if you're feeling good about your answer and you think it's right and it should be right, and for some reason this computer is not taking it, you can go back and you know, we're going to be dealing a lot with vectors. So finding these vector representations might be important. I think one big issue was a force vector that you guys needed to put in a capital F, and you put a capital F and it didn't want it. So sometimes you need to put this hat on, or the vector line segment on, to show that you are actually putting in a vector. So those are just a few things that, how should we call it? A few details that this particular system wants you to be precise with. All right. The other thing that might be important in terms of resolving a vector is with angles, and I don't know if there are any examples of that here. And here's one. Quarterback throws a football. Hey, quarterback. Did you guys watch the game? You just watch the commercials. Broncos. So let's try this one. The quarterback throws a football with an angle of elevation of 50 feet, or 50 degrees, sorry, and a speed of 70 feet per second. So that speed business will have to, something that we'll talk a little bit more, a lot more about later on. They want us to find the horizontal and vertical components, and by finding the horizontal and vertical components, we essentially will be able to find resolve the vector components. So what we have is a vector that we want to represent with not an x and y. Well, we want to represent it in terms of x and y eventually, but what we want to do is find the x and y components that it would make. So there's a horizontal and a vertical speed that we want to resolve. And so far what we're given is an angle of 50 degrees. And when they say the speed in this case, the speed will represent the length, and we'll talk about the length a little bit later on also. But the length is essentially the measurement of the actual arrow. So they call it magnitude also. Now it's direction and magnitude. So here's the other part of the vector. We have the direction that gives an angle of elevation, and magnitude is the length of the vector. All right. Well, once you know that, you should be able to find the horizontal and vertical parts of this by just using trigonometry. So we have the horizontal length as your x value, and we have the vertical length as your y value. And with some trigonometry, we should be able to find that. So I think the cosine is the one with the adjacent. So the cosine of the angle, cosine of 50 degrees is equal to the adjacent side. That's the unknown side that we're looking for over the hypotenuse side, which is 70. And so that x is equal to 70 times cosine of 50 degrees. And likewise for the y, the sine of 50 degrees is equal to the opposite over the hypotenuse. So y is equal to 70 sine theta. Does this look familiar? No, I don't care about physics. Does it look like something that we've seen before in this class? Close? Polar, yeah. So if you just look at this line segment as the radial distance r, this is x is equal to r cosine theta and y is equal to r sine theta. That's not a coincidence. It works like that because that's how it's defined. So I don't know if they want I'll round off your answers to one decimal place, so you know that you got to punch in and type in a number. If they don't have this round off your answers to whatever, then you want to make sure that you put in the actual value, the exact value they say. And so I was just going to type in 70 times sine 50 degrees here, but if they want the answers round off to decimal places, you need to punch that in your calculators. And make sure that you're in degrees, not radians. In general, we want to be in radians all the time, except when we do calculations with degrees. So just be careful with that also when you're plugging in your values. Okay, so that's another way to resolve your vector if you're dealing with angles and lengths, which we'll be doing a lot. Okay? All right, so I won't find an answer for that. Let's go to adding vectors. So when we're adding vectors, what we want to do is have a visual of what's going on, and then have the numerical and analytical stuff that we need to use to compute the addition. So in general, when we have a couple of vectors, we put them tail to tail. So you have this one vector, and then you say you have another vector. So when we have these two vectors, what we want to do is we want to add them. And we want to know what that's going to look like. So one important part in trying to do an addition of vectors or understanding addition of vectors is to try to visualize it and how it would look like. And when you add them, you really just add component by component. So let's do an example here where it's in 2 dimensions and then this can easily extend into 3 dimensions. So let's say B is equal to B1 comma B2, and C, or A, is equal to A1 comma A2. And I hope you're getting used to the notation where if I'm looking at a vector, then it's boldface, or in this case it's arrow on top, and if it's not a vector, then there's nothing on it. So the addition of these two would just be component by component, A1 plus B1 comma A2 plus B2. But it is, like I said, it is important to look at it from a geometric point of view to see how it would look like. And so to do that, what people do sometimes is they, instead of putting it tail to tail like normally what we would do, we would, maybe I should have done it the other way, we would have A, and then we would add B to it by putting the tail of B to the head of A and seeing where it points. I actually did it backwards. I said B, and then I added A to it. But like in everything that we've done so far in our lives, addition is commutative, so the order doesn't matter. And in this case, it doesn't matter either. So whether you do A plus B or B plus A, you're going to end up with the same thing. The point is, the new vector that you have can be represented geometrically as the diagonal of the parallelogram that can be constructed with these two vectors as its sides. So this is your vector AB. Okay? Any questions? All right. Well, the same is going to go for the subtraction. Well, I don't know if it's the same as going to go for subtraction, but we have a similar idea when we do a subtraction of vectors. Just going to grab my vectors. Oops, now it's a big mess. So when we subtract vectors, we almost do the same thing. We could take a look at those vectors from with the tails in the same spot. And then when we do, let's do, what should do, a minus b, or b minus a. And b minus a is going to be a new vector that would connect these two vectors. If we take the same requirements as when we did the addition, b minus a is going to be the first component subtracted and the second component subtracted. Now, subtraction is not commutative, so the order will be important, and you will get a different result depending on how you subtract. So in this case, b minus a will give you a vector that connects the heads of a and b. But the new vector that we have here has the head on b and has a tail on a. So you can think about it as a head minus tail again. But instead of looking at it as the points like we did in one of the examples that we did earlier, we're looking at it as the heads of the vector, the head minus tail. So when you subtract 5 minus 4, what's 5 minus 4? 1. If you switch them, 1 minus 5, or 4 minus 5, what do you get? Negative 1. So you get the negative of the value. So the same thing's going to happen when you switch to order here. It turns out when you subtract by switching the orders of the vectors, you're just going to get the exact same vector. Well, it won't be exactly the same anymore, but you're going to get a similar vector, b minus a, except it's been switched over. What does that mean? That means the vector that you get actually got switched around. Let's see if I could switch this around. A little bit more. There it goes. So it's the same magnitude as the previous vector, except it's going in the totally opposite direction. And this idea of having a negative in front of it, we'll talk about what that means when we talk about the scalar multiplication. Yeah. Okay. Any questions? All right, so that's the geometry behind the addition and subtraction. And some of the problems that are involved, I don't know, again, I don't know if it's in your homework, but some of the problems that are involved in in this section is to look at the arrows, the graphs. When you're adding or subtracting vectors, how does it look like geometrically? Okay, and so what you could do is you can put the two original vectors tail to tail, whether you put it in origin or not, it doesn't really matter. But if you put the two vectors tail to tail, and then the addition will just be the one of the diagonals, and the subtraction would be one of the other diagonals. Okay. All right. I think we can move on to scalar multiplication now. You know what a scalar is? That way we define a scalar?
It's a value without magnitude or direction.
It's a value, yeah, without
magnitude without a direction.
you could just, yeah, we could think about magnitude, but it doesn't even have to be magnitude. You could just say it's a numerical value. Technically, it's some sort of magnitude of something. But no, actually, it's not magnitude because magnitudes are always positive. So it has to be just a number. So a scalar is a numerical, and let's put non-vector. Because really that's the whole reason we're calling it a scalar, is just because it's not a vector. Another reason why they call it scalar is that they usually refer to it as the number that can scale your vector. Scale. What's scale? It's a number that can stretch your vector, scale it, make it twice as long, make it half as long, make it go the opposite way, stuff like that. So let's start with a vector again. Let's call this vector v. You know what? Maybe I'll change my vector here. So the vector 2 times v is a scalar multiplication operation of that vector. And so what I would do is I would take this vector and double it. So maybe I want to, looks like there's 2 vectors there, which is really what's happening, but I guess we want to make sure that we're doubling it. So it's just twice the size as the original vector. So that's what 2v should look like. And then half of v, we just shrink it half the way. And then the other type of scaling is scale it, make it go the opposite direction. So a negative 2v would just make that vector go the other way. Is it the same direction? My direction might have gone a little off here. So a negative in a vector in front of the vector will just make the values go the other way. And the math behind this, the simple math behind this, is just distributing the scalar for each component. So if, for example, v was equal to v1 comma v2, then a scalar, usually we use a Greek letter for a scalar, and then a v is equal to alpha times v1 and alpha times v2. Okay, so imagine this is 1, 5 or something like that, and then you scale it by 2, so it'll be 210. It'll just double. Or if you put a negative in front of it, it'll make it negative 1, negative 5. All right? So that's scalar multiplication. Now, we've spoken about magnitude already, and so let's talk a little bit more about, let's be more precise about the magnitude. And a magnitude is the length of the vector. So if we have a vector v, or w, or whatever you want to call it. Let's call it v. We want to find the magnitude of v. And for us to find the length of a vector, we can go back to the old Pythagorean theorem thing again. All right? At least in 2 dimensions, it seems like we can do that. So if we resolve this vector and find its components, this is your x component, v1, and your y component, v2, where v is equal to v1 comma v2. Then, to find the length, the notation for the length is this. We usually use double bars for the length of a vector. And this is going to be equal to, well, again, Pythagorean's theorem would just say v1 squared plus v2 squared. That's the square of that length. So if we want the actual length, we want to unsquare it or take its square root. And then that's your formula for the magnitude. Now, this is kind of like the distance formula in 2 dimensions. So if you imagine that we go into 3 dimensions, we'll have a similar distance formula in 3D. So in 3D, if you have a vector, let's call it W, then the magnitude of W is going to be similarly the square root of the sum of the squares. And notice it's all positive. Or 0 if all the components are 0. So note that this is all bigger than or equal to 0. Now, if you imagine this happening in 4 dimensions or 5 dimensions, we're not able to visualize that, but we can still deal with vectors in 4 or 5 dimensions, and we can find the quote magnitude or the length of a vector in 4 dimensions or 5 dimensions the same way, right? Mm-hmm. So all we need to do is add another component. WV, let's use U. U1, U2, U3, U4. And so the magnitude should be arrow when we're talking about a vector. Now, in higher math, you'll be going and diving into all these things and defining this length, this magnitude. This is just one way to define a magnitude, and this is a way to define a magnitude in Cartesian coordinates and in what they call Cartesian magnitude. Sometimes they call it something else, I forgot. But you can define the magnitude a slightly different way as long as it satisfies some certain properties of magnitude. We do have a magnitude in 1 dimension as well. You know what it is? Yeah, but when we're talking about the magnitude. If we follow the same process, all we're doing is we're adding the square of another component, right? So if we only have 1 component, just a scalar, right? So the magnitude of a scalar is the square root of a squared. That's also known as absolute value. So this brings me to some lazier notation that I might sometimes use. When I refer to the magnitudes of something in higher dimensions, I may just use a single bar, and you should understand that this is the same thing as a magnitude. So in other words, what I'm trying to say is that I want to be able to use single bars for the magnitude in two-dimensional vectors or three-dimensional vectors, and you should understand that it's the same thing. A magnitude is really just the absolute value, except when we're dealing with a vector, you're looking at the length of the vector. When you're looking at the absolute value, you're really looking at the length of that number on the number line from 0. And whether you're on the left side or on the right side, the length is always going to be positive. So it's the same business over here. Okay? So I know you guys are going to ask me one of these days when I'm doing some problem and I just use a single bar. You're going to ask, do you mean the magnitude? And I say, why, yes, this is the magnitude. I wonder who's going to ask. All right. Now, some interesting ideas with this magnitude now. There might be some times where we want a vector going in a specific direction of another vector that we know of, but we want to have it a certain length. And let's start with a certain length being 1. And for this, maybe we should do actual numbers. Let's make up a vector somewhere in space or in 2 dimensions. Yeah, we can go 3 dimensions if we want. Let's go 3 dimensions. Some vector in space with, let's say, 1, 3, and 4. As some vector in space somewhere. And a unit vector, whenever you see the word unit, you think of 1. So you might be curious to have this of length 1. Find a vector, let's call it u, in the same direction as v, given here, with unit length. In the same direction as v with unit length. So if we look at this and we can actually compute it, the length of v is equal to, what was that formula? Something with a square root, right? It's a square root of each of these components squared added together. What is this, 26 or something? So the length of this is square root of 26, which is clearly not equal to 1, and we want it to have unit length. So the way to make it unit length is usually we divide by that same quantity. So if we take v, and then you divide it by 26. So v is a vector, and divided by the square root of 26, the square root of 26 is a scalar. This doesn't really make too much sense. But it is really just a scalar multiplication, right? Division is the same thing as multiplication. So you can think about it as a scalar multiplication. And by definition, that just says to take each of those components and then distribute the scalar that we have. So we got 1 over square root of 26, 3 over the square root of 26, and 4 over the square root of 26. You should convince yourself that if this is u, the new vector now, you should work it out yourselves. that when you take the magnitude of this, that you are going to get this thing to equal a 1. You would do that by squaring each component and adding it, and you'll see that that should equal a 1. So I won't do that. I'll let you figure that out. Okay? Now, sometimes we might be interested in a vector oh, I just saw something here. That just proves how crappy my handwriting is. All right. Sometimes I might be interested in having a vector, and instead of making it unit length, I want to make it of length 10 or something. So let's see. What if I had my problem start like this? Find a vector W in the same direction as V with length 10 instead of having unit length. So a really common and easy mistake to make is to take this vector and multiply it by 10. And if you were to do that, you'll see that if you multiply everything by 10 and take the magnitude, that it's not, the magnitude is not going to be equal to 10. Check. Magnitude of V is equal to, W equals 10 plus, or not plus, 10 comma 30 comma 40, and then the magnitude of W is the square root of 10 squared plus 30 squared plus 40 squared, which I don't know. Anybody work this out real quick in their calculators or their heads? Well, let me just say that it's not equal to 10. So it's some value that's not equal to 10. Okay? So we know that this is not the right move for this. And what do we need to do? Any ideas? If you shrink it down to make it into a unit vector and then multiply by 10, then that should work out better. So the process for doing this is to find the unit vector first. And then scale by 10. Okay, so we already have the unit vector from before. And then you just need to scale it by 10. So our new vector is going to be 10 times the unit vector. And then that's it. Okay? So we got all the scaling down okay? Then if you want it going the opposite direction, throw a negative sign in front of that, then we're all good. So these are addition, subtraction, and scalar multiplication are basic operations that we do with vectors. The funny thing is that so far when we have two vectors, we can add them, subtract them, but we can't multiply two vectors yet. And so far the only thing we could do with a multiplication type thing with vectors is multiply it with a scalar. So to multiply two vectors, that's going to require a little bit more interesting work. And so there's, for our class, there'll be two types of multiplications of vectors. One of them is called a dot product. The other one is going to be called a cross product. And in higher math, there's other types of multiplication. In general, there's this thing called the inner product, which is kind of like the dot product, but you can define your own multiplication if you want, depending on what kinds of applications you're using it for. So our next step is the dot product. Before we do that, let me tell you that the dot product has another name. And it's sometimes referred to as a scalar product because the result is a scalar. So it takes two vectors and then the result is a scalar. So you got a vector dotted with another vector and then you get a scalar. So the dot product is sometimes called a scalar product for that reason. Our cross product is our other type of product that's going to yield another vector. So sometimes the cross product is called a vector product, but we'll get to that tomorrow. Okay? So there's two types of definitions that's usually presented with this. And some books present one as a definition and the other one as a result after the definition. I would just kind of like to call it two different definitions. Here's one of the definitions. And this one I call the algebraic definition because it does the algebra portion of it. If we have a vector, oh, my notation changed a little bit over here. So let me talk about this notation first. Oh, sorry. I'm going to put this definition on the next slide and then talk about this. Talk about the notation. That's not really just all restricted to the dot product, but back it probably should have been covered back before as we were talking about scalar multiplication. So the notation I vector, the j vector, and the k vector. So in two dimensions, the I vector is the vector 1, 0, and the j vector is a vector 0, 1. And there's no k vector in 2 dimensions. In 3 dimensions, the I vector is 1, 0, 0. The j vector is 0, 1, 0. And then the k vector is 0, 0, 1. So if you look at this in 2 dimensions, you got your ij vector as 0 or 1, 0 and 0, 1. 1, 0 for the I, and then 0, 1 for the j. And then in 3 dimensions, you have the I, the j, and the k vectors. Now these are unit vectors, and it's nice that they are perpendicular to each other, and they have special properties, but they are sometimes called a standard basis vectors. Standard basis vectors. And they're called basis vectors because they, in linear algebra, they form a basis. And what that means is that if you have any vector in 2 dimensions, you can always express it as a combination, scalar, multiple, and addition combination of I and j. And then if you have any vector in 3 dimensions, you can always write it as a scalar, multiple, and addition combination of I, j, and k. And the fancy phrase for that in linear algebra is that you can write it as a linear combination of I and j. What that means is that, let's go to 3D. If you have your vector v equal to 1, 3, 4, you can write that as 1 times I plus 3 times j plus 4 times k. And if you want to actually work that out and see how that works out, you got 1 times 1, 0, 0 plus 3 times 0, 1, 0 plus 4 times 0, 0, 1. And if you do that, if you carry on that scalar multiplication and addition, you should get your original vector back. So when you see the I, j's, and k's, those numbers in front of that would just fall as components, so you can write it either way. And to me, writing I, j's, and k's is just an extra step, but it's used a lot in the book and it's used a lot in physics, so sometimes that might be good. And especially if there's some zeros that are involved, instead of writing 0, 0, 5, some people just say 5k, and then they know it's 0, 0, 5. So that's the notation, IJK notation. That could be important for us. All right, let's define the dot product. Algebraically, the dot product is defined by multiplying the corresponding components together and then adding them all up. So U1, U2, U3, that's one vector. V1, V2, V3 is another vector. Then the dot product is defined by U1 plus U2, or U1, UV, U1, V1, plus U2, V2, plus U3, V3, added together. And when you do that, each of those components is a scalar. You multiply 2 scalars, you multiply 2 scalars, you multiply 2 scalars, you get scalars, you add scalars, you get scalars, and this is your result, is a scalar. Okay. So a simple example might be a vector u with 1, 7. Let's just do 2 dimensions, but you can this thing can happen in 3 dimensions just as easily. Vector v is -4, 3, let's say. So u dot v is equal to 1 times -4 plus 7 times 3. What is this? -4 plus 21 is 17. Okay. So that's the definition, quick example, nothing to it really. And the order isn't important because according to the definition we're doing some multiplication and addition, so if you switch the order it doesn't look like it's going to make much of a difference. So in this case we have something that is commutative. And this wouldn't be that big of a deal except our other product is not commutative. So we want to stress this idea that the dot product is commutative, and we'll see that the cross product is not. That's the algebraic definition. We have just enough time for the geometric definition of the dot product. So like I said, in some books, they say one's a definition and the other is some result that follows. I would just like to consider both of these as definitions. It doesn't really matter. But in some cases, the geometric definition becomes a little bit more important. The algebraic definition is a way to compute it. The geometric definition is where we get to start to apply this to a lot of different things, or whether it be in physics or in math. The idea of the geometric definition becomes important. So, the geometric definition here relates the dot product, and you may need the algebraic definition for that, the dot product with the lengths of those vectors and the angle between them. Theta is the angle between u and v. And here they also make a note that theta is an angle between 0 and pi. What is that? Let's see. We have 2 vectors, u and v. So what this entails is we look for the angle in between them, and and you find the magnitude of u and v. Now, realistically, you probably won't necessarily know the angle between 2 vectors right away, and then finding its lengths might, it's not usually the easiest thing to do. So this turns out to be more useful for finding the angle between them. So if we use these same 2 vectors, 1, 7, and -4, 3, we can actually find the angle between them. Right? So according to the formula, we have the dot product u dot v is equal to the magnitude of u, magnitude of v, and the angle, cosine of the angle between them. Now, since we have values for u and v, we can find the dot product. We actually already found it up on top here. We can find the magnitudes of them, and then here would be our unknown that we would be solving for. So let's work it out. Let's see. The dot product is 17. We saw that up here already. The magnitude of 1, 7, let's see, 49 and 1 is 50, square root of 50. The magnitude of negative 4 and 3, 16, 9, 25, right? And then the cosine of the angle between them. So all that's left for you to do is find theta, and that should be some cosine inverse of something. Times 5. Square root of 25 is 5, right? So cosine of theta. And theta is just the cosine inverse. So by finding that angle between them, that's sometimes that's useful for some of the things that we need to do or we have to do. So imagine if you have a cube. Cube is three-dimensional, right? Try to find the angle between an edge of a cube and the main diagonal of a cube. Think about that. It's not 45 degrees. So think about that. I was going to make it a extra credit, but that's really an easy problem to do. So think about that, and then we may address it at the beginning of the class next time. All right, so we got the definitions of the dot product, and we're going to do some applications and then jump to the cross product by next lecture.